Hello everyone. Thank you, Tiago Cruz, for accepting our invitation to deliver a talk for our research center, okay, AIDRC. The talk is the title of the talk is "The Enemy Within AB Using Built-in Automation and Control Systems for Covert Data Exploitation." I am Mohammed Amin Farag. I am lead researcher in cybersecurity. Okay, and Dr. Tiago Cruz will deliver a talk. I will just give a short view about Tiago Cruz. Tiago Cruz is an associate professor at the Department of Informatics Engineering of the University of Coimbra since December 2013, and where he obtained his PhD in computer science in 2012. Tiago is a senior researcher at the Center for Informatics and Systems, okay, of University of Coimbra, having started his research activity in 2001. His research interests cover areas such as management systems for communication infrastructure and services, embedded computing, critical infrastructure security, etc. He has been involved in various opening and industry-funded research projects related with cybersecurity, autonomous management, etc., and as well as several national projects in partnership with telecommunication operators and research agencies with both technical and management activities. Thank you again, Tiago Cruz, for accepting our invitation, and the floor is yours.
Okay. So first of all, I have to thank you for the kind invitation. It's really a pleasure for me to be here and to be able to deliver this talk to you. And I hope we will be able to exchange some nice ideas, because even the one who presents should be always ready to learn and learn from others. And questions sometimes are a very nice way of learning. So I was already introduced, and that's a good thing. In fact, I work with University of Coimbra in Portugal. Supposedly, we are the 12th oldest university in the world. And because of that, we have a strange uniform that is very similar to the one that you can see in Harry Potter movies. There are lots of jokes about that, okay? But anyway, it's a nice place. It's a small city in Portugal, very nice climate. If you have the opportunity to visit us, come and drop me an email message, because it will be a pleasure for me to basically meet you, okay? So, and the rest of the presentation was already done, so I can skip directly to the topic of this presentation. So this is basically the outline that I'm going to follow, okay? So a good presentation, I believe it's a story. So this is more or less the index of the story that I'm going to tell you. And I'm going to start, well, from, I believe it's the obvious starting point. It's about the old problem of protecting data. And it always comes to the same thing, isn't it? Because I will tell you a secret. In my previous life, before I went back to the university, I was a systems administrator. So I also got a feeling about how these things are dealt with, but from another perspective, from the practitioner perspective. And, you know, it always comes to the same problem. You have to balance. First, yes, you have stuff to protect, obviously, but you have also to balance that with how much it costs to protect it. And, well, there are information, there are things that you are going to protect it because you are mandated by law and the fines are high. So it's costly because the fine is costly. But sometimes it's not that the case. You want to protect information because it's sensitive. Trade secrets, intellectual property, and of course protection comes always at a price, and it increases along with the importance of the information that we want to protect. I think it's more or less obvious for you. So yeah, and there are standards to deal with this. It's good, okay? If you work in the intelligence community or are familiarized with the procedures that the intelligence community in the military often use, you know that there are standards and procedures well established to deal with this. And they're still, well, in the 21st century, they are still big fans of air gapping, okay? And they're not completely wrong, I believe. The problem is not about air gapping things, it's about relying only on air gapping to protect things. In fact, you have even two designations, okay, the SAPs, the security access, the special access program facilities. And these ones, this is the designation that the US military use. And usually these are the facilities that host information or infrastructures to house, I would say, sensitive information. But if you work with the intelligence community, the term and the designation is different. You call it the sensitive compartmented information facilities. But you know what? It almost comes to the same thing. For instance, if you work with the airspace industry and you are an external contractor, most likely, of course, it depends on the nature of the projects that you are working with, you are going to be probably mandated to have a secure room, okay? And that secure room is supposed to be air-gapped, disconnected from the network infrastructure of the building or the organization. And in that place, where, of course, you are going to have access control, you have a computer or many computers that are air-gapped, okay, with plans or information that only people with a certain level of clearance are able to access. This is the way it works. If you work with Western helicopters of Airbus or so on, well, most likely, if you are an external contractor, you are going to be mandated to have such a room. And only people with a certain security clearance will be able to access the room to basically check stuff, basically check information, plans, etc. So basically, it's to access sensitive information. But once again, it comes the question. Yeah, you have air gapping mechanisms and you have policies in place and you have regulations. And for instance, the Department of Homeland Security and the military, they have very nicely laid out regulations, very strict. But mostly they are based on this idea. I put a Faraday cage and I disconnect from networking, and most likely I'm going to have a secure air gap thing. And this is good, okay? But you already know the answer. There are limits to which extent air gap can be effective. Everyone knows the story about Stuxnet. Natanz was isolated. So what happened is that an external contractor was infected. So that was a game of patience. It took some time for someone from the external contractor to go to the facility within an infected pen. So it was a game of patience. But they couldn't go straight away to the target facility, so they went indirectly. So yeah, we know from past experience that air gapping has its own limitations. And then you have side channel exfiltration. And if you check on the literature, and this is only an example, okay, you have lots of interesting tricks that demonstrate to which extent we can steal information using side channels. Okay, let's be realistic. Not necessarily all these tricks in the list are feasible. For instance, there are some tricks based on electromagnetic interference leaks that are very nice and the proof of concept works, but it works like centimeters far away from the target. So probably not very feasible. They are proof of concept implementations. But others, well, are quite scary because, yeah, they can be used in the real world. There's a demonstration. I don't know if you are familiar with it, but some of you already saw it. There is a video on the internet. Basically, they created a Trojan that used keyboard LEDs, modulated information using the 3 LEDs. And what the guys used to demonstrate the proof of concept was to use a drone with a digitally stabilized camera that was focused on the keyboard, and it was getting the sequence of LED lightning, and it was using video processing techniques to demodulate the information that was being stolen. You might argue, but this is slow. Yeah, but if you don't have any other option, probably you are ready to accept that the only way, it's slow, but it works, okay? So, and this takes us to the main topic of our talk, building automation and control systems. And you know the old saying that everything that can be used can be abused. And I have to tell you, this is probably no exception, okay? Because, you know, modern buildings, modern corporate buildings, modern, university buildings are in fact smart buildings. And the smart part of it, it's not necessarily so smart, but it's smart enough to be convenient. It means that we have added automation to the building infrastructure. So yeah, because of efficiency reasons, because we want to create better comfort conditions for the people working there. So we have lighting that adapts automatically to the hour of the day and the external lighting conditions, and we have climate control that is automatic, even because we want to save energy. So we want to balance things, and smart buildings are perfect for that. But anything smart these days means that it has automation. And if any of you have already worked with automation security in the past, you know how messy automation can be, okay? Traditionally, the automation domain has been, you all know about the SIA triad, the confidentiality, integrity, and availability. And probably you already heard that for automation, it's the opposite direction in terms of priorities. And first and foremost comes availability. They designed for the 24/7. Security, it's not the first priority when it comes to automation. In fact, and probably you know, things are changing, fortunately, but this is a question of mindset, an old mindset. And this applies to industrial automation, but unsurprisingly, also applies to building automation. And you know what? Instead of just telling you that and asking you to believe me, you can go to Shodan. Everyone knows Shodan. And if you search for exposed equipment out there, and you go for Modbus, and everyone uses Modbus, whatever, and probably you will find PLCs, so programmable logic controllers, so technically it's conventional automation devices. Unfortunately, you are going to find them, but not only that, because it seems that in building automation, Modbus is also used. So if you look and you search, you will probably find interesting thing. And of course, if you are careful about doing your homework, that means open source intelligence or ZINT for you, you will find this sort of thing exposed on the internet. So this is a building automation automata. This is used to support basically climate control and lighting, and this supports, it uses a protocol called BACnet. Okay, curiously, BACnet is one of the oldest protocols out there, but not necessarily the most widespread. Okay, and surprise, no authentication, no encryption. Welcome to the 70s. Okay, so yeah, we have this sort of thing exposed. So the old problems that we already identified with industrial automation, well, they still exist on building automation. So this is really difficult. So yeah, and what does this has to do with the air gap? Well, you already know what happened with the air gap in industrial automation. At the beginning, most of the equipment was, well, black boxes. Little was known about protocols, internal operation, architectures, and it was believed that this was the good way, the proper way of doing things. So hiding, treating them as secrets. Well, everyone, at least anyone who has worked in cryptography knows that, in fact, what you need is exactly the opposite. Because if you have an encryption technique for which you disclose the entire technique and algorithm and still is safe, that's proper security. But unfortunately, this is the automation mindset, black boxes. And it worked, okay? Of course, not necessarily for all cases. You always have insider threats, and that's a different problem. But okay, that was fine until people decided to connect automation to the internet, and that was a disaster, and to IP networks, and it was a complete disaster. So, well, that said, there's the question, okay, to which extent the lessons from industrial automation can apply to building automation? Well, they can. One of the most widespread protocols out there and technologies, because the KNX also specifies the physical layer. So it's not only a logical protocol, in fact, it's almost the entire OSI file stack. It happens that one of the standards, KNX, it's one of the most popular and widespread, and you have a consortium that basically keeps up and updates the standard. It's formed by lots of manufacturers, well-known names, okay, big names of the industry, like Siemens, for instance, and so on. So they are part of the KNX consortium, and it emerged in the 90s. Okay, originally it was not called KNX, it was called the European Installation Bus Association, but then they decided that, okay, they needed to standardize things, so they created the KNX standard. And what is KNX? Well, KNX is a building automation technology that uses a twisted, well, it can use power line and wireless, but the most conventional form and widespread form of KNX is based on twisted pair, okay? So you have basically a twisted pair, okay, twisted pair cabling operating at 24 volt, and it's a shared bus where you connect sensors and actuators and everything that you need to connect together or on a building automation network. For instance, and of course you have provisioning procedures. Why? Well, you buy, imagine, an intelligent switch and you have a light fixtures. So how do you associate both? Well, you have software for that. If you are a certified specialist, you will have access to the software that is used to provision and configure devices. So basically you say, look, this device, when a message from this device appears, it's going to be read by that device, and that device will know that, okay, it has to light up the fixture. So this is the way, basically, in a very simplified way, how you configure a QNX network. You basically pick the devices, you configure them, you provision, you associate messages and addresses. This has addressing, it's a shared bus, and you have addressing here, and that's the way it works. Well, on a big building, okay, things, of course, tend to get more complicated. Well, most of the installations are physical medium. It's twisted pair for you, okay? But you can use power line, not as widespread. It's basically used on those situations that you cannot afford to legacy buildings where you cannot afford to install twisted pair. You can use infrared. I don't advise you to do it. Even Ethernet IP, but really old school and the most old widespread version of QNX is twisted pair. And you know, for a big building, this starts to get interesting. So what I'm going to show you here is how a real-world KNX deployment works. So you have lines. Lines is a shared bus entity where you can have up to 64 devices, and you have two types of addresses, unicast addresses and some sort of group addresses. It's similar to multicast. Basically, you provision devices to belong to a group address. In this way, when a message is received on the shared bus to that group address, the devices that are assigned to it will receive a copy of the message. This can be used, for instance, if you have a switch that you want to operate several light fixtures simultaneously. What do? Basically, you create a group address, you associate the light fixtures to the group address, and then you say, when I press the switch, it will send a message to the group address wherever, and the light fixtures will be controlled this way. But you can go further away, because usually a line, you use it for a floor or eventually for a small home or apartment. But what if we have a big building? Things start to get interesting, because you can have bus couplers and line couplers. Line couplers are used to connect lines to each other. And then bus couplers are used to connect lines to the backbone line. So, for instance, on the building, on a multi-floor building, you can have, for instance, one line per floor or more, if you need so, connected by line couplers. And then you have on each floor a bus coupler that will connect to the backbone line. This allows you to create communication also between floors. It might be desirable for several use cases, okay? And you can connect up to 15 areas to a backbone using couplers. By the way, line couplers could theoretically and can theoretically block traffic between lines, but for reasons that have to do with the way they are implemented, usually they are very limited in terms of memory, so you cannot load them with lots of rules. But yeah, you can implement some sort of protection there, okay? So, and this is how KNX framing works. So, you know the lessons from Modbus and so on. Well, it's the same thing all over again. So you have a very simple framing structure that until quite recently, you don't have encryption here, you don't have authentication here. There is a standard called KNX Secure that was introduced a couple of years ago, but unfortunately, most deployments don't use it. And even for recent deployments, it happens something that unfortunately it's quite common, that integrators, despite the fact that they have these capabilities at their disposal, they don't use it because they assume that it's an extra layer of complexity that they don't want to deal with. So even for modern buildings, quite often we will find devices that support KNX Secure with encryption, but it's not being used. Okay, so, and this is very simple framing structure, very easy to understand, very easy to decode. So yeah, it's bad. Even if we went forward with KNX Secure, there's a problem that you have thousands of legacy buildings that you are not going to retrofit, except if you have a very good reason, or you are willing to spend the money to do it because you want to protect something that it's worthwhile. The question is that you might argue, but is it that dangerous? Unfortunately, is. We already have incidents in the past when, for instance, hotels had compromised access to rooms because someone decided to hack the KNX network. Yes, because the smart locks were also connected to KNX. So yeah, even conventional incidents where people are locked in places or someone gets access to places where it shouldn't have access at all already happened. In fact, it's documented on the literature that it happened with Google headquarters in Australia, and it was unfortunately due to KNX. Now imagine this. Let's back to the original problem, the air-gapped room. I'm going to tell you a sad story that unfortunately already happened. Once upon a time, there was an air-gapped room. Ethernet didn't reach there. It had a layer of metal on the walls to create a Faraday cage. But, and don't ask me why, it was within a smart building, and someone decided that it wasn't necessary to disconnect or isolate the control of the lighting and climate from the rest of the building. So you know what? The KNX twisted pair network reached the secure facility. Yeah, let me repeat this. You had a twisted pair cable that basically went through the floor, connected devices to the KNX bus, and also was within the secure facility. So you already know where this is going. And it's a shared medium, let's not forget that. So imagine this situation. If an attacker manages to deploy 2 KNX transceiver devices on the bus, it can use basically to steal information and get it outside of the secure room. But, well, theoretically, we know this is possible. But we decided to go a little bit farther away, and we decided to create a proof of concept. So here you have it. It's called Alfred, and Alfred basically it's look, the picture is misleading. It's very small. In fact, you can hide it within a wall socket. Okay, the case for the wall socket, it's small enough that you can hide it there. And what you have here is a microcontroller with the implementation of the KNX stack together with the KNX transceiver. And we created this to prove to which extent it was possible to exfiltrate information inline using the KNX bus. And you know what? Not only we did that, but we have our own test beds. In fact, not only we have our own small test bed on the laboratory, but we got access to 2 buildings, one residential building and a hospital, okay? Of course, we didn't play with anything sensitive. And we tried to understand to which extent it was feasible to steal information using the KNX bus, and to which extent it was doable without disrupting the normal operation of the bus. So we did some experiments, and we cannot say that we broke a speed record. We didn't, but I have to tell you, it's quite encouraging, because yes, it's possible. And moreover, I can tell you that using these rates, we were able to send information inline on the KNX bus without disrupting normal operation of the system. Because it's one of the things that you must be very careful. You don't want to disclose your presence by creating a denial of service on the KNX bus. So you shouldn't abuse the throughput, otherwise you will hamper the functionality of the smart building itself. But you know what? It's possible. It works. Okay, it's doable. But we decided to go a little bit further. What if we don't have a secure facility? It's just a secure place, but not necessarily one that wishes to comply with the standards and so on. And we want to do something similar to the exfiltration case that used the keyboard LEDs. What if? So we decided to do implement another exfiltration use case that used KNX on a different way. So we assume that the receiving end is not necessarily within the building premises. So, okay, so let's put the scenario together. We have information that we want to steal, but not necessarily so important that it requires a special room, a closed room with no windows. So we have windows, okay? And I can't control KNX stuff on the building, but not necessarily I want to deploy the receiving end within the building or within the line for several reasons. It might happen that I don't have a nice place on the floor to deploy the receiving end. So what can I do? Well, I can do it indirectly. It was already shown in the past. You can use lightning to steal information. In fact, you have lots of interesting use cases. There is a team that used the infrared LEDs from security cameras to exfiltrate information to the outside of the building. It was very clever. Usually, you put security cameras on a separate VLAN. So what they did, they discovered that the infrared LEDs that were used for night vision features were controllable by software. So you know what they did? They managed to get to the VLAN, to the IP camera VLAN, and some of the IP cameras that we used for surveillance were placed on the outside of the building. So you know where this is going. Basically, they used modulation. They modulated the infrared LEDs of the cameras during the night. They were able, with a camera, a tripod, good stabilization, they focused on the cameras and they used blinking, so basically LED blinking, to control to modulate information and steal information out of the building. So we can do the same thing with KNX, because look, KNX is one of the big use cases for KNX is lightning control. Okay, so not only that, but it happens that lots of modern control mechanisms for light fixtures are designed for LEDs, for LED ribbons or LED strips, or for LED illumination. So if you check on the catalogs, it's interesting because lots of those controllers implement pulse width modulation, because this is the proper way of dimming a LED. It's not with a solenoid, is the old school with a variable resistance, because it's not efficient. It doesn't work the way it should, or you expect it to work. You do this with PWM. And it happens also that these controllers also support, curiously, solenoids or single phase motors, because some of them can also be used to control ceiling fans, because you can use PWM also to control a single phase motor. So it's curious, because these features are quite versatile, in fact. So imagine this: you have a light fixture, it uses LEDs, and let's not assume we have RGB lighting, because if you have RGB lighting, that's even more interesting, because you can use tones and colors to modulate information. So let's just assume that we have a regular fixture and you can control brightness. I think it's enough. Most of them allow you to control brightness of the lighting fixture. So imagine this: you put Alfred in the next to the place where you are going to steal the information, and Alfred is going to transmit the information on the KNX bus, but not inline. What it's going to do is to pretend he's a switch, and he's going to send messages to a light fixture control to basically use brightness variations to encode bits. It's not fast, but it works. So, and this is basically what we did. We played with dimming, and we tried to understand to which extent it was feasible to use dimming of LED lighting, KNX control LED lighting, to steal information. So it's the old setup. You have something on the inside that is stealing information, and it's modulating the information using brightness variations on a light fixture. And then you have a camera on the outside of the building, on the other side of the street, that is focused on the room. It's capturing the video, and then you are going to process the video to decode the information that was originally modulated. And what we did was we used a series of techniques, and we settled up to differential pulse position modulation. And so it is simple to encode, it is simple to decode, and we use this to modulate bits as variations of brightness on the light fixture. And we did some proof of concepts at 4 meters distance and 15 meters distance. And this are not best cases for a very simple reason. If you have a light fixture on the ceiling and the walls are white, it will happen something that is very nice for an attacker, is that you can focus your region of interest on the entire window, because reflection on the white walls will diffuse and amplify the effect. So it makes it even easier to decode the modulated information. But we decided to do it this way. So the origin of interest is smaller. And we try to understand if by controlling brightness pulses at a speed that was not noticeable to the human eye, it was possible to steal information. Well, let's go straight to things. Basically, we get video, and then we all use video processing. We basically apply the old techniques. We take off noise, we apply some blurring, we average the image, and then we get this. And this is very nice, because it's basically a time series where it's very easy to see the pulse differences of the PPM modulation. So yeah, it's doable, and it's doable at 15 meters distance, and if you have ideal conditions that are in fact more common than ours, fixture on the ceiling, it will be even easier. So we did discover that it was possible. We had played with regions of interest on the video capture to see if we could optimize this. Let's just insist on this part. We didn't implement sophisticated modulation. We didn't implement error control or error recovery. We don't have anything of that, okay? And we just tried to prove the concept, okay? So it's not a speed breakthrough, but you can do it, okay? It's possible. In fact, we have a more recent proof of concept that is way faster. Anyway, yes, we could steal information using brightness, pretty much like the old use case that use the keyboard LEDs. Inline techniques are faster. Okay, if you want to steal a Bitcoin private key or SSL private certificate, it would be possible, and it's possible. Okay, so yeah, exfiltration is feasible, and if you are really focused on stealing information, of course you are going to improve the techniques. So now we get to the next part of it. How do we defend against this? Well, nobody cares about building field buses when it comes to security. That's the starting point. Really, nobody cares. Integrators don't care. So yeah, it's overlooked when it comes to security. So, but what we can do? Well, there are certain things we could do. One of the things, it's kind of obvious, most likely, we could try, since we are working with a shared bus, to analyze traffic and try to create some sort of, you guessed it, a network intrusion detection system. So yeah, we try to create one, curiously using the same hardware platform as Alfred. And our KNX network intrusion detection system is designed to do two things. It surveils the KNX network, but it also does the same to the Ethernet network where the provisioning station or configuration station might be. Okay, so we try to get one eye on both sides, not necessarily because we expect lots of traffic will appear on the Ethernet side, but sometimes what happens in modern automation is that you have a permanent Ethernet gateway that is used for provision and configuration purposes because it's easier. You don't have to travel with adapters and couplers and so on. So we did it in the way that our proof of concept device basically surveils, monitors both sides. And this is basically our architecture. It's implemented on an embedded system, a single board computer. And in fact, one of the first versions used a Raspberry Pi 3, if I'm not mistaken, 3B. And well, we proved it was possible, okay? We implemented a taxonomy that includes, these attacks are very similar to the ones that you already know from the IP world. So the scan, that is the device scanning, I'm trying to search things on the network. So this is a line scan attack. The device info attack, when you query device to get further details about it, sometimes the attacker doesn't knows that the device is there, but doesn't know what the device does. So you need to query it. And also the message injection attack. Another thing that we do, we try to learn context information. For instance, when you have motion sensors, usually you have sequences that appear naturally. A fixture only lightens after a motion sensor is triggered. So if you see a sequence of messages, commands that are out of order, either you have a malfunction or something strange is going on. Okay, so and we try to basically implement these attacks. Okay, including also an invalid context attack. This case where out of order things appear, and we did this using two different approaches. The first one, we based on snort syntax, we created our own rule description technique that allows you to create manually signatures for someone who provisions an infrastructure to be able to describe security rules to protect the building. Okay, this is nice, but you already probably understood that this is also cumbersome, because if you are going to write lists and extensive rules to protect all possible cases, well, you are up to a big pile of work, believe me. But we implemented it. And of course, you know how rules are in IDS. The good rules are usually quite effective for the cases where they were designed for. There's no argument against that. But we also implemented, besides the rule detection, and we tried to adapt the rule syntax to the KNX context, we also created an automated learning model. Of course, learning, let me just tell you this and reinforce it, doesn't take place on the device. It means that we have a learning phase that has to do with the provisioning of the IDS, where we get traffic from the line, the KNX line, and we try to learn nominal patterns, okay? Nominal operation patterns that characterize the functioning of the system. And this way, yeah, we are able to get the best of both worlds. And this IDS is quite effective. But just to finish this talk, I will tell you one of the most disencouraging things about this. It works, we solve a problem, we are also able to get inline exfiltration attempts and so on. But then comes a hard question. Can we sell this? And now it's the moment where we learn one of the most important lessons, and usually I reserve this to the finish. Why? Look, when you want to sell a product, okay, let's just get back to the first slide. How much it costs to protect something versus how much you have to lose. Let me tell you, after talking with lots of integrators and friends and so on, I got to the conclusion, and it's kind of obvious, let me tell you, that despite the fact that this thing works, there is no market for it as a standalone device. This is the way it is. You have, except for very few specific cases, you have no market for a standalone IDS. Yet, you have market for this if you can sell it integrated within an existing offer. And that's different, okay? So basically, this is what we learn. So it's doable. You can steal information using building automation. And yes, you can also protect the building infrastructure from that, even legacy, especially legacy deployments. But when it comes to selling this as a product, and where the real world calls back and you have a reality shock, you don't have a selling point for it. And basically, you don't have a selling point for it as a standalone thing. But you might have a selling point for it if you manage to integrate it within a service offer. That is, you have, imagine an integrator that tells you, I'm going to offer this service, I'm going to provision the entire infrastructure, install the equipment, and so on. And within all of this that I'm going to offer, including maintenance, I'm also going to include a security service just in case. In this way, it's feasible, okay? But if we don't go this way, forget it. We don't have a product to sell. So, and I finished my presentation here. So I'm open to your questions and even suggestions, okay?
Thank you, Tiago. Thank you. Thank you. Thank you for your excellent presentation. Very happy to attend this seminar. So let's see if you have some questions in the chat. Okay, so we have some questions. Okay, so the first question is, what are the most common vulnerabilities in BACS system that attackers can exploit for data exploitation?
In this system, well, it's let's put it this way. First, no authentication, no encryption. So if you want even to imagine that you have KNX intelligent locks, you can lock people on the room. Okay, so you might not want to steal information. You might want to lock people on the room. You can do it. And that's another problem. You have lots of bridges that usually are part of the deployment that are used for configuration and management. Usually a KNX twisted pair to Ethernet bridges. And usually those bridges are an extra vulnerability vector, because most bridges are there to perform a very simple thing. Bridge Ethernet with KNX because it's easier to use the ATS software. It's the name of the software that is used for provisioning and configuration, to configure all of that stuff just by connecting to an Ethernet network. Well, it happens that most of these gateways are very unsafe. It's, you know, we have that in automation. You have the RS485 gateways to Ethernet that at a certain time were very widespread and common in automation. And these gateways, most of them, if you search on the internet, I'm not going to name manufacturers, are riddled with bugs and insecurities. Well, here is the same. Okay, so you just can go directly to the twisted pair bus and attach things and send commands and examine commands. You can go to a gateway. You have lots of attack vectors here, okay, that unfortunately I would risk that in more than 90% of the cases are exposed.
Yeah, it's very clear. Thank you. So the second question is, does the dimming technique have more bandwidth than the unframed technique?
No.
No.
We can improve it, okay? We can improve it, and it's possible to do certain things, but no, for a very simple reason. And I will tell you why. Because the rate of commands that you use to control dimming is limited by the maximum rate on the bus, on the KNX bus. So you cannot exceed that, basically. Except for one case, but this is theoretical, okay? Is if you are able to reprogram if the dimming fixture is reprogrammable and has extra features, okay? In some cases, you might improve bandwidth, but not exceed what you get in line.
Okay, excellent. Okay. So the next question is about machine learning. I don't know if your intrusion detection system is based on machine learning. And the question is, how can machine learning be integrated into a BACS system to detect and prevent attacks? We know that machine learning has the potential to detect attacks and identify potential threats in real time. But how we can ensure that machine learning algorithms are properly training and tuning to detect malicious activity?
Okay, so I will tell you what we did, and I will speculate on what can be done.
Okay.
What we did was very simple, because we were using a Raspberry Pi. What we did was we did capture and training on a good machine. We created the models, and then we deployed the models on the Pi. So inference takes place on the single board computer, but not training, to be fair. But if you have edge computing, for instance, that's a different matter. You can have a more continuous procedure in the sense that probably you can have capture being done, okay, and you can always be improving the system with time and improving the technique. But for our proof of concept, no, we didn't do that.
Okay. So this is the last question. Okay, I will ask another question from my side. So as you know, we can use blockchain technology. So blockchain can provide tamper-proof and decentralized ledger that could enhance the security and integrity of BACS data. So, so I used it before, and I deployed blockchain for Internet of Things and infrastructure. But I don't know. I never proposed it for this system. So, according to your opinion, how can blockchain be used to secure BACS system, okay, and prevent data exfiltration?
Oh, that's a nice one. I will tell you a story, and probably you are familiar with it. KNX Secure specifies the mechanism for encryption, but surprise, it doesn't specify the mechanism for with the equivalent to a PKI, a public key infrastructure. So you don't have mechanisms to share or exchange keys. It's everything is done manually and statically. It means that if you compromise keys, you have a problem. So I believe probably that blockchain could be used to create an extra layer of trust to manage this shortcoming, okay? So even for KNX Secure, most likely blockchain could be a very interesting answer to solve that problem.
Yeah. It's very clear. So the last question is, as you know, we use now blockchain and machine learning, AI for security and provide the security requirements, authentication, confidentiality, integrity, etc. So how can we ensure that machine learning blockchain are not themselves vulnerable to attacks?
Oh, well, that's a problem. Yeah, especially if you look at machine learning from a more generic perspective within security, We will always have the adversarial thing, isn't it? So if you have a minimum of knowledge about the models that are deployed, you can try to design attacks to go around them. So that's a tough one, because it's the old problem of the mice and the mousetrap. We are trying to make better mousetraps, but the mice are getting smarter. So that's really a big problem, because here in this scope I didn't play with adversarial techniques, but in other scopes I did it in the past. And if you have minimum knowledge about what is being used, you can design attacks, tailored attacks to go around that. And for me, it's scary, because it means that you, as a defender, you must be aware that eventually you might have to assume something. This is scary, but probably it will become a fact of life. Even if you don't have proof that your information, the models are known, you should assume they will. And design security as some sort of DevOps things, that you assume that security is not something that you deploy and monitor, but something that you develop and improve continuously. This is the way I see it. And I see no other option. Okay, it's a cycle.
This is an area of active research and development, and currently we are trying to understand the potential benefits of and challenges of this emerging technology, machine learning for blockchain, cryptography for security, and also we are working also now how to secure AI. Okay, we can use AI for security, but now how to secure AI? Okay, this is a big challenge.
This is very nice, really, and I see a lot of interesting challenges there. To be fair, lots of nice intersections. Very nice, really.
There is another question, from our colleague. The last question. Are these attacks assuming an insider threat that will deploy an agent with the air-gapped network?
The attacks usually assume that you have an insider, but look, the insider can appear in different ways. Sometimes it's, once again, the game of patience. Sometimes the insider was there when provisioning was made, or the insider was there when maintenance was undertaken. Sometimes it really depends on the way the attack is designed. Sometimes you can start with social engineering. You can create a problem that doesn't exist to justify that someone needs to go there to fix the problem. So sometimes it takes imagination to design a good attack. It doesn't require for an insider threat to be permanently there. That's the bad news, I would say. But of course, it requires at least to have access to the building for a certain time extension.
Thank you again for your excellent presentation. I love this seminar. And see you again. Thank you very much.
Thank you for our questions, and thank you for the invitation. It was really a pleasure.
A pleasure. Thank you.
Thank you.
Bye, Tiago.
Bye.